We all know that stress can, make your hair fall out. We've all heard that.
Sure.
But this deep dive we're doing today, it reveals something much, much more critical. It shows that acute stress doesn't just cause some temporary shedding.
No, it doesn't.
It leaves behind a permanent biological scar, basically setting a tripwire that primes your body for a future autoimmune attack.
That really is the core of it. I mean, clinicians have always linked stress to autoimmune flares, but the actual mechanism, it was always kind of vague.
A black box.
Exactly. So our mission here is to trace the precise, step-by-step causal chain. We're going to look right inside the hair follicle, which has these two key cell types, the quiescent stem cells and then the rapidly dividing transit amplifying cells.
And the big question was how a single burst of stress could so selectively target one but not the other.
Right.
Okay, so let's start at the beginning of that chain, phase 1. What's driving that immediate tissue damage, the hair loss you can see just days after the stress?
Well, the researchers first had to figure out if it was nerves or something else, like general hormones.
How did they prove it was the nerve?
They
Wow.
took them out. They proved it by removing the nerves themselves.
Oh, wow. Okay.
The initial damage is driven purely by your sympathetic nervous system. That's your fight or flight system.
Right.
Acute stress just puts it into overdrive, releasing this massive local burst of a neurotransmitter called norepinephrine, or EE, right near the hair bulb.
And when they destroyed those nerves?
The hair loss was completely prevented. And they found that this NE burst acts on the hair cells through a very specific switch, the beta-2 adrenergic receptor.
ADRB2. So the nerve signal is hitting everything, but only the rapidly dividing cells are actually dying. That must mean they have some kind of unique vulnerability.
They do. They're metabolically distinct, and that makes them selectively fragile. Using intravital imaging, so watching this happen in real time in a living animal, they saw the specific killer. That norepinephrine surge triggers a rapid, just massive influx of calcium inside those vulnerable cells.
A calcium flood.
A calcium flood, yeah. That huge overload just overwhelms the cell's mitochondria, their power plants, and that leads to cell death.
So it's not the stress signal itself, it's the calcium flood that's the actual killer. And they proved this by using a blocker, right? Something to stop the calcium.
Exactly. They used a chemical blocker, and it prevented the cell death entirely.
Okay, so here's a thinking question for you listening. What kind of cell death is this, and why does that distinction matter so much for the immune system?
And this is, I think, the most crucial step in the whole paper.
Right.
This isn't a controlled, clean cell suicide, apoptosis. This is messy. This is necrotic death.
The cell just bursts.
It just bursts, and that's highly inflammatory because when it bursts, it releases all of its internal contents, which act like chemical alarm bells for the immune system.
So those alarm bells, the damps, they start the autoimmune clock. How does that local tragedy turn into a body-wide immune threat?
Well, specialized immune cells, a type of dendritic cell, immediately rush in and they capture that necrotic hair debris.
They clean up the mess.
They clean it up, and then they migrate to the lymph nodes. And there, they basically teach the killer T cells, the CD8 plus T cells, to recognize and attack hair follicle components as if they were an invader.
And they proved these T cells were primed for attack.
Oh, yeah. They transferred them into immune-deficient mice, and those mice had an immediate hair follicle attack.
But wait a minute. In a normal mouse, the T cells are primed, but they don't attack right away? That seems wrong. Why would they wait?
It's because of peripheral tolerance. It's like a powerful security system that's still keeping everything calm. The initial necrosis, it sets the landmine, it primes the T cells, but those cells are still locked down.
So you need a second trigger.
You need a second trigger.
Yeah.
The full-blown autoimmune destruction only happens later if the follicle gets hit by a second, totally unrelated inflammatory challenge. That second hit overrides tolerance, and that's what finally lets the T cells launch their attack.
This is just exceptional. What this paper gives us is something incredibly rare, a complete, targetable, step-by-step causal chain from a physiological event, acute stress to, well, the start of an autoimmune disease.
It really moves that whole stress causes illness conversation from just a vague idea to concrete, targetable mechanisms. We now have specific molecular levers to look at, the sympathetic nerve activity, that deadly calcium surge. It could reframe how we treat these conditions.
Okay, so let's boil it down. 3 crucial takeaways for you. First, acute stress kicks off this process by using sympathetic nerves to flood very specific vulnerable cells with calcium.
Second, the way those cells die is key. It's a messy necrotic death, and that inflammatory debris is what's used to prime the immune system for a future fight.
And third, this proves the two-hit hypothesis. The initial stress is just the first hit that sets the tripwire. You need a second, later inflammatory event to actually trigger the full autoimmune attack.
And it leaves you with a final thought. This whole study focused on acute stress, a single big event. But think about the chronic, low-level stress so many of us deal with daily. How might this same pathway, this subtle norepinephrine and calcium signaling, be quietly fueling the long-term risk for autoimmune diseases across all kinds of tissues over decades?
Something to chew on.
Welcome to the Everyday Journal Club. I'm Hope, a biologist with 15 years of research experience, now fortunate to be working in a Nobel Prize-winning lab. This channel has three main goals. 1, to help you stay effortlessly updated on the latest scientific breakthroughs. No paywalls, no jargon overload. 2, to build a supportive community where we can exchange the most valuable experience-based research advice. 3, to share valuable strategies and concrete examples on how to achieve meaningful scientific breakthroughs. Once we reach 1,000 subscribers, I'll begin releasing content focused on the third goal. Let's go! Let's make great science together.